So far, when we've been finding the integral of a function, we have been looking at something that's actually called an indefinite integral, and starting today, this lesson, we're going to be looking at definite integrals, and to get us started with that, we're going to investigate Riemann sums. At the end of this lesson, you'll be able to find the Riemann sum of a function on a given interval. All right, first of all, just before we get started on a Riemann sum, I just want to clarify what I'm talking about with indefinite versus definite. If I have an integral that looks like this, let's say just says x squared dx, we could easily just take the derivative of that. We would get 1/3 x cubed plus c, and we always put plus c because it's a general solution. Okay, what we're going to do when we move to a definite integral looks something more like this, where I'm going to go 1 to 4 x squared dx. So notice now this time I have limits. When I do that, what I'm really going to be looking for, if my answer is x squared, that's what the curve x squared looks like, I'm going to be looking for the area under the curve from x equals 1 to x equals 4. So when I take the antiderivative and I have boundaries, it's asking me to find an area under the curve. So what we're going to be doing before we actually get into any sort of rules is be looking at a Riemann sum. Okay, you'll notice that this definition is pretty lengthy and kind of confusing, but I would like us to look at this part of the definition right here. And I'd like you to just look at a few things. This sigma notation, that is telling us to find the sum of a bunch of different things. We're gonna add up what we find when we do this part of the problem. And this says f of c, well remember f of anything is just a y value. And delta x is just a change in some x values. So basically what we're going to be doing is taking the change of an x value times a y value, and then we're going to be adding all of those answers together. Okay? When in plain English, basically what we're going to be doing, we're going to be taking a figure that looks like something like this down here, and what we're going to be doing is breaking it up into rectangles, and we're going to find the areas of each of those rectangles, and then we're going to add those areas together. And notice you can kind of tell that from this formula because we have an x times a y, which would be the area of a rectangle. Okay, so let's go ahead and do this. Okay, we're going to approximate the Riemann sum for this graph here. So we want to approximate the area underneath that curve using a Riemann sum. And this time we're going to use the midpoint of 5 subintervals of equal length. Okay, there are 3 types of sums that I can find. I can find a left endpoint sum, a right endpoint sum, and a midpoint sum. And I'll show you what that means in just a minute. First of all, 5 subintervals means that I need 5 rectangles. And this is how I will always start a Riemann sum problem. So I want to know how the width of each rectangle, and this is the easiest way to do that. I need to get from 0 to 50. And if I have 5 subintervals, the distance between those two, 50 minus 0, would be 50. And I need to break it up into 5 intervals, so the width of each interval is going to be 10. So now I can actually put that on my chart. So basically, this is just getting me set up for the first rectangle will go from 0 to 10, the second one will go from 10 to 20, third one will go 20 to 30, then 30 to 40, and 40 to 50. Okay, now when I'm doing this, I need to know how tall to make the rectangles. That's where the midpoint comes in. Okay, from 0 to 10, the midpoint of 0 and 10 is 5. So that's going to, whatever's happening at 5, that's going to dictate the height of my rectangle from 0 to 10. So notice it looks like it's about right there. So my first rectangle is going to look something like that. Okay, my second rectangle is going to go from 10 to 20. And the height of that will be dictated by what's happening at 15. Notice 15 is right there. So that's going to be the height of my rectangle. Okay, my next one will go from 20 to 30. And the rectangle from 20 to 30, the midpoint is 25. So what's ever happening at 25 is going to dictate the height of that rectangle. Okay, and then from 30 to 40, the midpoint would be 35. So the height of that rectangle is dictated by what's happening at 35. Okay, and then from 40 to 50, the midpoint is 45, and at 45, it looks like, there we go, that's the height of my rectangle. Well, let's go over a little bit more. So you'll notice I have 5 rectangles, and what we're going to be doing is finding the areas of each of these rectangles, and then we're going to add them together, and that will approximate the area. Notice it does give us pretty close. We have a few things that are left off from it, but it at least will give us a good idea of what the area under that curve happens to be. Okay, just for ease of working this, I'm going to give each rectangle a letter. So to get the area of rectangle A, the width of that rectangle will be 10, and the height of that rectangle is going to be whatever's happening at 5. So if I look at what's happening at 5, the y value is 12. So the area of that rectangle will be 120. Okay, for rectangle B, the width of that rectangle is still 10, and the height of that rectangle is what's happening at 15, and what's happening at 15, the y value is 27. So that will be 270. Okay, rectangle C, the width of that rectangle is again 10, and then the height of that rectangle is what's happening at 25, and the y value at 25 is 70. Okay, then rectangle D is going to be what's happening at, the width again is going to be 10, and then the height will be what's happening at 35. The y value at 35 is 81, so that area will be 810. And then finally rectangle E, what's happening, the width again is going to be 10, and then the height is going to be what's happening at 45, which happens to be the y value is 60. Okay, so now what we're going to do, we found those areas. Now we're going to be adding those up, and when I do add those up, I will get 2,500 as my area. Okay, one thing that I want you to notice, they all were being multiplied by 10, and if that happens where it's an equal length of an interval, that doesn't always happen, but if it does happen, there was another way that I could have written this. I could have written it as 10 on the outside, and then I could have done 12 plus 27 plus 70 plus 81 plus 60. Okay, and another way that I could have written that, as long as we have equal intervals, which we did, we could have kept the 10 on the outside. Where did I get the 12 from? It was what was happening at 5. So I could have put v of 5 plus v of 15 plus v of 25 plus v of 35 plus v of 45. Okay, so all of these different ways would be equally acceptable to show your work. I'd need to show either actually adding up the rectangles, or setting it up this way, or actually setting it up this way. And this way actually will be one of the best ways to work it, where you're just showing what you're going to do, and then I'll be showing you on your calculator how you can let the calculator do the work for you. All right, let's try another one here. This time it says to consider the graph of f of x equals 5 over x squared plus 1 on the interval 0 to 3. And we're going to approximate the Riemann sum using the right endpoints this time of 6 subintervals of equal length. Okay, I'm going to attempt to do this one without drawing a picture. Basically what this is asking us to do is find the area under the curve, or find the integral from 0 to 3 of my 5 over x squared plus 1 dx. And I do want to put dx just to let people know that my variable is x. Okay, basically what I'm going to do, without even having to draw the rectangles, I know there will be 6 rectangles and I will rely on the right endpoints. I'm first of all going to draw that chart that I drew on my last problem. I know I'm going to go from 0 to 3. So the distance between those two, 3 minus 0 is 3. And I need to break them up into 6 subintervals. So 3 divided by 6 would be 0.5. So each one of them is going to have a distance of 0.5 between them. So we'll have 0.5, 1, 1.5, 2, 2.5, and 3. So that's what my chart's going to look like. Okay, so when we do this, I could actually do 6 separate rectangles, but I'm going to try this a little bit differently this time. Since the intervals are equal length, we know that the width of each one of our rectangles is going to be 0.5. So we can just write 0.5 on the outside. Okay, now when I'm talking about a right endpoint sum, the first rectangle is going to go from 0 to 0.5. So the right endpoint, the right part of this interval would be 0.5. So I need to find out what is happening at 0.5. And the way that I would do that is plug that into my f equation. So I'm going to have f of 0.5. And then I'm going to have plus f of, this time my second rectangle is going to go from 0.5 to 1. And the number that's on the right side of that rectangle is x equals 1, so I'm going to find f of 1. And then plus, my next rectangle goes from 1 to 1.5. The number that's on the right side of this interval would be 1.5, so I'm going to find, to get the height, we'll find the y value at that spot. And then from 1.5 to 2, the right endpoint would be 2, so we'll find f of 2. And then plus, we are going to go from 2 to 2.5. And to do that, the right endpoint would be 2.5, so we'll calculate f of 2.5, and then plus, if I'm going from 2.5 to 3, the right endpoint would be 3, so I'm going to find the y value at 3. So that would be my setup. Okay, from here, we're going to let our calculator do all the work on this, and I'm actually going to show you in class a faster way of doing this. But for right now, basically what we could do is we could plug 0.5 in here and get an answer, plug 1 in there and get an answer, plug 1.5 in, get an answer, plug 2 in, get an answer, plug 2.5 in and get an answer, and plug 3 in and get an answer. When I get that whole answer, I will multiply by 0.5, and I will come up with 5.114. Okay, and again, we will discuss in class how you can get your calculator to do all this work for you so it's not tedious with you having to plug everything in and possibly making a mistake in between. All right, one thing that I do want to go over is the definition of a definite integral. What's going to happen is delta x approaches 0 in the Riemann sum formula above. So basically, as the rectangles become skinnier and skinnier, there should be less space or less gaps that we're leaving. So what the Riemann sum is going to do is becoming a definite integral. It's going to become the actual area of the region, the skinnier and smaller we make our rectangles. So hopefully now you can use a Riemann sum to find the definite integral of a region.